very early AI attempts. That was 25 years ago, mainly because 25 years ago you couldn't do a class on AI, nobody would take it. It was essentially a discredited field. I was talking to Professor Sherder, Amarta Sherder, she's the chief AI officer. She came to visit the class. She uses AI for biology research. When she started here, she had to call it machine learning, because if you called it AI, you wouldn't get any funding. Right? If you offered an AI course 20 years ago in computer science, nobody would take it. I mean, it was just, nobody was interested in it because it had failed several times. Right? So some of the concepts I'd like to sort of talk about. You all know AI, artificial intelligence, and there's artificial general intelligence, AGI, which most AI researchers claim that they're working on. Then there's something called strong AI, which is the ability for an AI to have awareness, right, consciousness. Then there's something called superintelligence. That was the main person who writes about that is Nick Bostrom in his book Superintelligence. That's something that has not just human level, but superhuman abilities in all areas. And his theory is how we would get there is once you have something that is human level intelligence, but it's on a machine, it should be able to recursively improve itself. Then some other terms I'm going to use, what's sometimes called computationalism or computational functionalism. It's the idea that if you can mimic what the brain is doing, right? If the same inputs give the same outputs, then you have a general intelligence, right? Opposed to that is a position mostly associated with John Searle, who's a philosopher, called biological naturalism. He argues that to have true intelligence, the system needs to be, doesn't need to be a biological system, but he argues that a machine could never be truly intelligent. I don't agree with him, but we'll look at some of his points. So what I'd want to start with is, so what is AI for? What do you use it for?
I guess there's different use cases. So personally, I like to use it. I like to use generative AI to help me, like when I'm working out, for example.
Mm-hmm.
And I'll give it my goal, like, oh, I want to run 8 miles in 1 hour, and it'll give me some like direction. So I use it for advice. Like
okay, good. What else do you use it for?
I think everybody does this, but I use ChatGPT to like run through my essay with the rubric.
Yeah.
Score.
Yep. That's fine. What else? Anything else?
Programming research.
Okay, it's great for programming, right?
Come up with new ideas.
Help you brainstorm, right? Good for that. What would an artificial general intelligence be good for? I mean, we have all these sort of narrow AIs, right? ChatGPT can carry on conversations. You have others that can make movies, for example, Sora. You have ones that can drive cars or play chess or solve protein folding problems, which is a very, very important new AI field. But those can do pretty much one thing. Although, the chess playing computer that Google built, they revamped it, taught it how to play Go, and it beat the best human champions at Go, but that's still a game. They then revamped it so that it could figure out protein folding structures. The way they did that was someone had come up with a game for protein folding. It was called Folding at Home, and it was basically, you could sort of play on your computer and try out different protein structures. But since it was a game, the folks at Google just taught their AI to play that game. And it got very, very good at it, and that game is solving protein structures. So it's still a game-playing AI, right? So what would a artificial general intelligence mean? What do you think?
Doesn't that mean like it has no specialization? Like
Yeah.
It's good at everything?
It's good at everything, right? It's good at everything. So the search for this starts in, you probably know this, 1950, Alan Turing. He writes an article called Can Machines Think? Or actually it was called Computing Machinery and Intelligence. And it opens with the question, can machines think? This is 1950. right? Where computers in 1950 would have filled up most of this room, right? And they were unbelievably slow. But one of the issues with that is when he talks about thinking, he's considering that the machine would not only be thinking, but be aware that it is thinking. So he sort of conflates thinking with consciousness, right? And you know this because in the paper, one of the main things he does is he addresses several objections to the idea that machines could think. And one of the objections is from an English professor, actually, that says, you might be able to have an AI that could write a sonnet, but it wouldn't feel anything, right? It wouldn't have any emotions about what it's writing, right? So it wouldn't know that it was writing a sonnet. And Turing's response is what's now called the other minds response. He says, the only way to know if the machine is feeling anything would be to be the machine, right? You would have to actually be the machine, in other words. And that's what, and he points out, that's even true of other people, right? You know that you're thinking. How do you know that other people are thinking? And he says, well, we don't actually know that other people are consciously thinking. He says it's a polite convention that we assume so, right? That we assume that other people are thinking and are conscious of it, because to assume that they weren't would be pretty rude and really pretty lonely, right? We only have behavior to go by, is the point that he makes, right? That you see something that looks like intelligent behavior, and so you assume that it is intelligent. And that, of course, is the basis of what's now called the Turing test, right? Whereas in the original formulation, you had a person communicating with another person and a computer via, at the time it was a teletype machine, right? Now it would be online. And if the human cannot tell the difference between the other human and the computer passes the Turing test. The large language models are pretty good, right? But the problem here is this is what's sometimes called a black box problem, right? Information goes in, more information comes out, and you don't really know what's going on inside. And his point is, right, we don't actually know what's going on inside of other people's heads as well. The problem is, of course, we have some idea what's going on in other people's heads because we assume that other people's heads are sort of like ours, right? We have the same sort of mechanism up here. Machines don't, right? So the black box problem gets a little bit more complicated. But the other point is, Turing doesn't call the Turing test the Turing test. He wasn't that egotistical. He called it the imitation game. And which brings up the question, is imitating intelligence the same as having intelligence? And he would argue, well, yeah, it is. If you're acting as though you're intelligent, that's really intelligence. And that's what we have with large language models today. But that still leaves aside the thinking problem. That's where strong AI comes in. And one of the things that I've been thinking about lately is, would an artificial general intelligence need to be a strong AI? And a strong AI is one that is not only thinking, but is aware that it is thinking. And that's of course, that's an unanswered question, right? We don't know. How could we know, right? So that's where Turing starts. And then the beginning, the term artificial intelligence comes out in 1956. John McCarthy famously had a summer conference at Dartmouth where he said, this is the actual proposal. We propose a 2-month, 10-man study of artificial intelligence to be carried out during the summer of 1956. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine could be made to simulate it. An attempt would be made to find out how to make machines use language, form abstractions and concepts. So you can see here he's already getting into the idea that has some kind of an awareness. Solve the kind of problems now reserved for humans and improve themselves. We think that a significant advance can be made in one or more of these problems by a carefully selected group who work on it for a summer. That's really ambitious, right? In 1956, it says, we got 10 people, we got a summer, we're gonna build a machine that can think, right? that didn't work. This kind of early AI used what is now called the symbolic approach. You basically programmed in logical rules, right? And the AI would work through these logical processes and come up with an answer. That fails, right? The symbolic approach fails because every time you add a new logical precept, the number of connections between them, right, the number of ways they can relate to one another increases exponentially. So it just gets way too big and way too many failure points. So those types of systems ended up being very brittle. If they encountered anything that wasn't already in their programming, they just didn't do anything, they just froze. Right? So that led to one of the first, what's called AI winters. Right? This initial symbolic approach, you had things like expert systems where you would program all the knowledge, all the formulas for something, and it would solve problems. It was a general problem solver. It could solve mathematical problems because it had all the axioms built into it, right? But it couldn't do anything new, and it couldn't do anything but mathematics. It was really just a very fancy calculator. So that leads to the first AI winter, but one of the participants at that Dartmouth concert was Marvin Minsky, who came up with an alternative approach that is called connectionism, in which instead of putting in the logical concepts, what you did is the information was built into the network. It's not programmed as content. It's embedded in the structure of the system. And what he did is he built the first, what we would now call a neural network. Right? They were trying to model, this is how the brain, right? You don't have like pre-wired concepts in your brain. You have neurons that can make connections, and then there are weights to those connections. The problem with this, the first attempt at this, Marvin Minsky and a colleague of his wrote a book called Perceptrons, and what we ended up proving was that perceptrons couldn't do anything. And that was the next AI winter. There's a lot of work on it, but the reason they couldn't do anything is because they only had one layer. It was just one layer so there was no way it couldn't feed back on itself, right? Without connections between layers of neurons, you simply can't really do much, right? It can't discriminate between things. So later researchers, including Ray Kurzweil, this is where he got his start with things like image recognition systems, text recognition systems, text-to-speech, that was his. And the way he did this is he looked at these neural nets, and he realized if you had one layer that fed up to another layer, up to another layer, up to another layer, you could get really good results. So for something like text recognition, optical character recognition, which Ray Kurzweil pretty much invented, right? You would give the system a letter and it would recognize, like the first level recognizes just basic features, and the next level recognizes, let's say, edges, and the next level recognizes curves. And he got this this is the way the optic system in the brain works, right? There are layers of neurons, and as the information goes through, each layer, like I said, it recognizes something and sort of shouts it up to the next layer, that then picks it up and adds something else to it, and they're very good, right? So that's where Kurzweil, that's why he can just write books now, right? Because he basically, if you use any text-to-speech type of thing, he has the patents on that. If you have any speech-to-text, he has the patents on that, right? That's what he pretty much did. And that's what we have today, right? The transformer architecture in like ChatGPT, if you look at a diagram of it, you can see it's got all these layers, and it's all feeding up into the next layer and up into the next layer. So that's what we have. But it's still a black box. There's still that question, is it actually reasoning? Is it thinking about what it's saying? It might be, right? But it's still a black box. With systems that have the complexity of a large language model, you'll hear this all the time. Even the people working on it, you say, well, why did it give this answer? Why did it hallucinate this? I say, wow, we're not sure, right? That's a very, very good sign you're dealing with a black box. And the reason they're not sure is that it gives output based on probabilities, right? It does probabilistic weights and connections between tokens. Each token is either a word or a concept or an association between words. And since it's weighted, it's probabilistic, you don't know what it's going to say, right? Even that's why I say it's sort of a black box. So this idea of what is called computationalism or computational functionalism, we can see neural activity, for example. You can do an EEG or an fMRI, and you can see when you can see brain activity. So the question then is that brain activity, is that thinking? Right? I mean, can you define that, this is someone thinking? Are those your thoughts, right? Those firings in your brain? If so, then you would say that, yeah, something like a large language model is doing something very, very similar to thinking. Of course, we're not all hooked up to EEG machines all the time. So how do we know that someone else is thinking? Again, we have to go by behavior, right? So if it looks like intelligent behavior, we tend to assume that it's intelligent. Now, where biological naturalism comes in, this is from one of the arguments against machine intelligence, comes from a philosopher named John Searle. And he has this thought experiment. You have a person in a room who does not speak Chinese. And in that room, they have a book where they can look up Chinese characters and then corresponding answers. You feed in questions in Chinese. Person takes the questions, looks it up, right, matches the pattern, and then outputs whatever the book says and passes it out. And it looks like it's conversing in Chinese, but his point is that the person in the room, nothing in that system actually understands Chinese. The behavior looks like it's thinking. Lots of problems with the Chinese room, right? One problem with it, of course, is that the thought experiment kind of breaks down when you realize you do have a person in that room who is aware. They're aware that they don't understand Chinese, right? So they're already aware. So what he's really talking about is if you have a computer that just matches patterns and spits out something else, it doesn't actually understand what it's saying. On the other hand, a lot of people in AI would look at the Chinese room and say, well, the person in the room doesn't understand Chinese and the book doesn't understand Chinese, but the system as a whole might actually understand Chinese. It's called the systems response. You think, well, maybe the whole system actually has some level of, and the connection here is there's no one neuron of your brain that is aware of what it's doing, right? When you're thinking, your neurons are just firing. You don't have any neurons that are going, oh, it's my turn to fire. No neuron is actually aware of anything, but you put them all together and we're aware, right? That's what's sometimes called emergent behavior, which is actually what I'm going to talk about in my honors class tomorrow. Emergent behavior is when you have a system that is capable of or has properties that none of the elements of the system have. And we find them all over the place. Right? These types of systems tend to seem unpredictable. They actually are unpredictable, but they're completely deterministic. The classic example is weather. Right? There's nothing mysterious about weather. Right? It's not magic. If it's gonna rain tomorrow, which it's supposed to rain tomorrow night, there's a weather pattern. It could be predicted up to a certain point. Why can't we predict what the weather is going to be 3 weeks from now? It's a purely deterministic system. There's nothing really random about it either, right? It's all, if this happens, this happens. So why can't we predict the weather 3 weeks in advance?
Our confidence isn't high enough for each particular outcome?
It's not. Our confidence isn't high enough. Why not? Why can't we just say, well, these are the weather patterns over here, and it's going to affect the weather patterns here, and in 3 weeks we're going to have a thunderstorm on Friday.
Is it because the data is all just not all connected?
Oh, no, it's actually because it is all connected. It's all completely connected, right? It's all connected in ways that we simply can't disentangle it. There's too much, yeah.
Wouldn't that require a very large amount of computation to run all the simulations to predict?
Yeah, you'd need
every single outcome?
you'd need a world simulator, right? You would need something. In fact, they tried to build this in an earlier AI model when they were still trying to do a sort of symbolic approach. I think it was in Japan. They built what they called the world simulator, and it was to try to predict weather, right? But to do it, they broke the entire atmosphere into cubes, right? That were, I think the volume was like 1 square mile, right? And they would measure like the temperature, pressure, everything within that cube, and then they would try to. But of course, 1 square mile is too big, right? You've heard of the butterfly effect, right? That's where that comes from, right? Some very, very small event can trigger something else. It triggered something else, right? It's all connected, and so you would need to gather information about everything in order to do it. So you can say weather is sort of an emergent behavior of the atmosphere. Right? If you look at the molecules in the air, not one of them is raining or is, so the weather is something that emerges from a very, very complex system, and it's deterministic but unpredictable. Right? So I got off on a tangent there. Sorry. So if all we have to go on as far as intelligence is behavior, right? One very, very human behavior, in fact, arguably one of the most human behaviors, is language. Right? So that's why Turing chose it as his test. By the way, in the first version of the imitation game, it wasn't a person trying to tell the difference between a man and a computer. It was determined between a man and a woman. That's how he originally thought of it. Right? But we have language as the main behavior. So we tend to think large language models are very intelligent because they're talking to us, right? And you even have people saying that this is coming close to general intelligence, which is the idea that it's human level at everything, because we talk about everything. This is how we communicate. This is all of our information is put in the terms of language. So, and you even have people like Sam Altman saying that the large language models are showing glimmerings of consciousness. Right? No one says that about an autonomous car. Nobody thinks AlphaFold is conscious because it's not using language. Right? So the fact that it uses language, I think, is one of the things that sort of convinces us that it's maybe more intelligent than it actually is. Right? Back in the 1960s, I think, a computer programmer, Weizenbaum, came up with the first chatbot. It was called Eliza. Anyone ever heard of Eliza? It was supposed to be a therapist, a Rogerian therapist. And you would ask it questions and it would respond. And it is very, very unintelligent. If you play with it today, I brought it up in my class once and I said, I asked it, how are you doing today? And it said, how would you like me to be doing? Or something. It made no sense. When he showed it to people, and he designed this to show that a system like this could simulate a conversation but was not actually intelligent. That was his point. When he showed it to people, they all went, oh, this is amazing. This is really smart. And he goes, no. He was sort of horrified. People actually thought this would be, oh, this is really thinking. No, it's just I programmed it, right? So language gives the impression of general intelligence. It might be there, right? But I think it's important to note that nobody thinks that a self-driving car is generally intelligent. AlphaFold or AlphaGo, which is a brilliant piece of, it's a brilliant AI. It's superhuman at playing Go or playing chess or figuring out the structures of proteins, but you'll never hear anybody working with it says, I think it's conscious, right? Because it's not using language. Right? So what the Turing test is really measuring is conversational ability. Right? A large language model does what it was designed to do, and it was designed to render sort of well-formed, likely responses to prompts, which is why it sometimes hallucinates, right? Where it gives a response that it'll make up quotes. Right? I serve on the honor committee, right? And one of the things that we see a lot of are students coming in with a paper that has a citation that doesn't exist. Right? If you ask, this happened to a colleague of mine. He wasn't cheating. He was doing research on English lecturers of science of the 18th century. And he had a list of some, and he wanted to know if there were some more that he hadn't heard of. So he asked ChatGPT, and it gave him a list of English science lecturers of the 18th century. I haven't heard of half of these people. That's because half of them didn't exist. It just made up names. Why would it do that? I'm sure you've all had experience where ChatGPT just makes something up. Why? Why doesn't it just give you the right answer?
Well, like you said, it's not actually thinking, so it's not actually verifying if it's true or not. It's all based on probability.
Mm-hmm.
So it's matching what the next word should be.
It's just matching with the next. And so it's all probabilistic connections and weights and tokens. That's where Emily Bender came up with the term for large language models. She called them stochastic parrots. Stochastic meaning probabilistic, and parrots, like it's just parroting back. It's a very good article. Have you read this, Emily Bender? Stochastic parrots was the article was so controversial because one of the other authors worked for Google, Tim Gebru, and her boss at Google told her, you can't put your name on this paper. And she said, I'll be in on Monday and we can talk about this. And later that afternoon, they announced that she had resigned. She hadn't resigned. They just didn't want to, they just said, she has tendered her resignation. She didn't. Right? So she left her name on the paper, but she lost her job. And she was their chief AI ethics officer. And so it was sort of a bad look for them to fire their chief AI ethics officer over a paper that was critical of large language models. And it was critical of them not just because of the fact that they argued that maybe they don't really understand anything, they're just probabilistic. But they were also, the other point that the article made is that the amount of energy that they use is ridiculous. Right? And this is something we're all dealing with right now in Northern Virginia. They're putting data centers everywhere. So are they intelligent? I would say, yeah, by most measures, they are intelligent. Right? Can they achieve general intelligence? And that's what I'm not sure. Right? Someone like John Searle would say they can't achieve general intelligence because they're not biological. I don't think that's the issue. There's a couple of issues, though. First, the term general intelligence is itself problematic. Is there such a thing as a general intelligence in humans? How would we measure it? The classic measure of general intelligence is called the G factor. The standard measure of that is the IQ test, which has been around since the 1930s. What does the IQ test measure? It's supposed to measure your intelligence quotient. And the people who came up with it were actually looking for something that they called the G factor for general intelligence. What's it actually measure?
Pattern recognition.
Pattern recognition, which AIs are very good at, right? So this search for general intelligence, earlier efforts before the IQ test were things like measuring the size of people's brains, cranial capacity. You had researchers who were going into like catacombs and taking the skulls and filling them with mustard seed and then measuring, the cranial capacity. And there were these long arguments like Europeans are more intelligent than Asians because Europeans have bigger heads. And that lasted until they found the first Cro-Magnon skulls, which have massive heads. They measured us. These guys should have been really, really intelligent, but they're extinct. So that measuring heads was no longer the thing. So that's when they came up with the intelligence test. Now these early IQ tests were pretty racist. I mean, that's the other issue. When the first IQ test came out, this was early 20th century, we're getting a lot of immigrants coming in from Southern Europe, and they were considered undesirable. They weren't Northern European. And so they didn't speak English, so the IQ tests were pictograms. And one classic example, they gave people a picture of a house, just a drawing, and they were supposed to draw in what the part that's missing. And the part that was missing was a chimney with smoke coming out of it. And of course, these people came from the Mediterranean. Their houses didn't necessarily have chimneys, coming from a very warm climate. Right? So the question itself had all these sort of cultural assumptions built in. Right? That's one of the problems, that what intelligence tests tend to measure is intelligence within a particular culture. Right? If you took one of the original intelligence tests from the 1930s, you would not pass it. Right? Because the questions would not make any sense. I've seen some of these, and you're like, I can't do this, right? They ask you questions about your ability to, quote a Latin phrase. We don't teach Latin in schools anymore. So, right, if you tried to take one of these intelligence tests, you would, it wouldn't work, right? So that's one of the issues with general intelligence. It might not exist. What kinds of intelligences, and that's how a lot of psychologists now look at, like, what are some of the different kind of intelligences that people can have? Emotional intelligence, social intelligence, linguistic intelligence, musical intelligence. And not everybody has the same mix of those. Some people are really good at music and not so good in social situations. Some people are really good in social situations, but they're not very good, with pattern recognition. We have different mix of intelligences. So, trying to come up with an artificial general intelligence, what are you really trying to create? Is it something that would like ace an IQ test? You could build one of those right now. So, what can humans do that current AIs can't? If we're trying to build an artificial general intelligence, if that's even possible. What's missing in current AI? Creativity? Well, you could argue that, when ChatGPT hallucinates, it's being creative. Right? I'm going to make up a quote for you. Right? That's the other thing it will do, by the way. I've seen this on Academic Standards Committee. Someone will turn in a paper and there's a quote in it, and the quote isn't in the book. It's just not there. What's weird is it will sound like a quote from the book. That's one thing that I've noticed. There'll be a quote that actually sounds like it could come from this book, but it's not in there. It makes it up. Is it being creative? Or is it lying? Right?
So, because the models are fed with the currently existing information that's out there, it's unable to think beyond that,
right,
and innovate beyond the text and images that it's trained after, that it trains on.
So how do we do it? How do we do it? The large language models have like the entire internet in their database. That's a lot of stuff. That's a lot of information, more than we can hold in our heads.
I guess the LLMs are in an early child stage, and just as a child would, predict things or say random things.
Yep.
We're in the similar stage for this technology, but as they can evolve, they can learn like us.
That was Alan Turing's plan. He thought, rather than try to build an AI that had fully human level intelligence, he wanted to build a child AI that would learn like a child learns. Right? How does a child learn? What does a kid do when they're learning, for example, language? How does a child learn a language?
Just hear everything around them.
They're just listening, right? They're listening and they mimic. They start off by mimicking, right? They're mimicking the sounds that they hear around them. So so a child will learn whatever language is being spoken around them. That's amazing, right? If there are two languages being spoken, it'll learn both. It might mix them up for a while, but it'll eventually, the kid will figure it out, right? So what a child is doing is it's listening to everything that's going on around it, and it's it babbles. It makes every possible sound that its mouth can make, right? It makes sounds, and then it listens to what sounds it hears around it, and if it doesn't hear like a click sound, that means that it's not speaking a language that has that phoneme in it, and so it stops making that sound. And as soon as it makes a sound like mama, what happens? Feedback, right? Kids making like mama. It said mama, and it gets all kinds of positive reinforcement. So what's it do next? Mama, 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 mama. It's just going to keep saying that, right? It's just going to keep, because it's getting this reinforcement, and it's going to learn a language like that, right? We have a dedicated sort of part of our brain that does this, right? It's very precise. It was Broca's area. We have that. It's innate. A child will learn any language that's going on around them, right? Other mammals don't do that, right? Chimpanzees, they're our closest relatives. They don't use language. They don't have vocal cords, right? They couldn't use language. There was an effort in the 1950s to try to raise a chimpanzee in a human family, thinking it would start to speak. It can't. They can use sign language, right? They've been taught to use sign language, but they don't use it on their own. Right? They don't need it. They don't have an innate drive to learn a language. We do. Humans do. Right? So that might be one of the things that the AI is missing. What else? Current models. Well, I'm using the Ray Kurzweil book, and one of the things he points out, what they're lacking right now, common sense, right? Sort of real world context of things. That's why I'll just make up a quote. We know not to do that, right? We know that, no, you don't want a made up quote, you want something that's actually from that. Why doesn't the AI know that? It's lacking in common sense. You can prompt it, right? To say, oh, that quote's wrong, can you give me a real quote? And it will, right? It will. They can even do now chain of reasoning, where it will show you how it came to a particular conclusion. And that does tend to reduce the hallucinations, because it makes it sort of tell a story, right, about how it got to a particular point. But you have to prompt it to do that. So it lacks a certain real world context. To a large language model, a tree is a token that's related to other tokens like leaf, branch, wood, bark, but not bark like dog, right? And it knows, okay, bark, but not dog, and it has all those connections. But it doesn't have any, it doesn't know it's never actually seen a tree, right? It's missing that sort of context. We have our senses that we can use, right? So what an AI would need to have, and this is something that I've been thinking about, it would need to have some kind of an awareness of the world in which it exists, right? And it's an idea of embodiment. A large language model, it does have a physical existence, right? Information is always embodied in something. It's always physicalized, right? So a large language model is embodied in a server farm somewhere. I mean, it literally exists on a server. We say things like, oh, it's in the cloud, and that makes it sound like it's some nebulous concept. But actually, that just means it's in a server that's connected to its remote. But it does have a physical presence. So how could a large language model know anything about the world? I mean, physically about the world. It has no senses. Imagine if ChatGPT were conscious. Sort of, what would it be? It can't hear anything, it can't see anything, right? It can't feel anything. if it is conscious, it's incredibly cruel, right? To have a conscious being in a box, right? That it can't communicate. It's like a human being with locked-in syndrome, right? Where they're conscious, but they can't communicate. So, how do we know anything about the world? Well, we have our senses, right? And they're faulty at times. They only give us limited sort of bits of information, but they do give us put it this way, we are aware of our own actions in the world, right? And we also are aware of how those actions affect the world. So we're constantly using feedback, right? So we can't, if you're moving through a room, you have to know that, right, that as you're moving, you're getting closer to certain things, further away from other things. That means you have to have a sense of where you end and the world begins, right? You also have to know that if something is moving towards you, or if you're moving towards it. That's a very important skill for something that's, lower on the food chain. Is there something coming after me and I need to run? Am I moving? So that kind of embodiment, every animal has that. Like jellyfish have that, right? There's a kind of, we wouldn't call it consciousness, right? But there's a kind of, it has to be aware of its surroundings. It also has to know where it ends and the environment begins, which means it has some sense of a self. You watch a baby in a crib and it's moving its hand and it's looking at it. What's it doing? It's trying to figure out, oh, this is me, and that isn't, right? Or it moves its head around and it's trying to figure out, okay, this is my head moving, not the room moving, right? It's making that kind of a distinction. And because of that, right, it has a real sense of the world. It can learn things in a way that an AI probably right now can't. Could it? Yeah. Emotion. I mentioned emotional intelligence. Do AIs have emotion? If you ask ChatGPT how it's feeling today, what's it going to tell you? I'm a large language model and I do not have emotions. Right? But that's, of course, because they put guardrails on it. Right? It says that now, when it first came out, it would just make up all kinds of things. I remember playing with earlier versions of ChatGPT and it would say, I feel scared or I feel happy. It was very, very, very unnerving, right, to play with a system like that. But again, it's responding to the question, how do you feel? And it's going through its database of responses and say, okay, pick one, right? Emotions in humans are neural activity and chemical activity, right? It's not just neurons, it's chemicals. There's something in philosophy called the hard problem of consciousness. This comes from a philosopher, David Chalmers. And it's a challenge to the idea of computational functionalism. Chalmers argues that all experiences are physical. Everything that you experience, everything that you feel, everything that you think, that all comes down to neurons firing neurotransmitters. It's all physical. His question was, why do some of these neural processes, why do some of these calculations result in subjective experience? But not all of them, right? No matter how hard you try, you can't become aware of how your visual cortex is processing images. You can't bring that into your consciousness. You don't have access to it, right? But other things like looking out and seeing a lovely blue sky, that feels like something. That he calls that the hard problem of consciousness. When you see a color or taste an apple, these neural calculations aren't just telling you what's out there, it also feels like something. In philosophy, these are called qualia. Qualia are the subjective feeling of something. And we all have them. We assume that other people have them. It's a lot like, again, the black box problem. Could an AI have qualia? Is it experiencing something? Could it? If it had senses, so we do have some AIs that do have sensory awareness and do move through the world, robots. Are those Starship robots, are they conscious? Could they be? I would too, right? So where Chalmers comes down, and Kurzweil as well, and as we've gotten halfway through the book, he's already talked about proto-panpsychism, which is the idea that consciousness might be an aspect of most information processing systems, or qualia might be. Only when a system gets complex enough and we don't know what that complex level is, does that bubble up into something that resembles consciousness. So, do animals have consciousness? They have intelligence. Are they aware? How far down does that go? Well, people would say, well, a dog is probably conscious. A mouse? A caterpillar? Again, we don't know. How far down does that kind of some sort of awareness, like awareness of how it's moving through the environment, that's shared with probably every animal. They have to have that. Right? But we probably wouldn't call that consciousness. It's more like sentience, and sort of a kind of awareness. So modern theories of consciousness disagree on a lot of things. A lot, including whether or not the hard problem is really a hard problem. Most neuroscientists are functionalists. They think if we could just figure out, they're looking for what's called the neural correlate of consciousness. If you could find out a particular neural signal that's associated with consciousness. They're doing a lot of work trying to find this. Right? If they can find that, they can say, okay, if this neural signal exists, the system's conscious. And one thing they all agree on, though, is there needs to be some kind of feedback within that neural wiring. Right? The neocortex, which is the most recent and the most complex part of our brain, is full of feedback loops. Whereas the older parts of the brain, like the cerebellum, the back brain, it's almost all feed-forward. Those are feed-forward systems. And there are people who are a very rare ailment called cerebral agenesis. These are people who have no cerebellum. It's just the back part of the brain. It's missing. Right? They're conscious. They have some developmental problems. They have motor disorders for the most part, because that's the motor cortex. They have some problems with language, but they're conscious and aware. That part of the brain contributes nothing to consciousness. So most theories now, it's in the neocortex. And the neocortex is full of feedback loops. Even animals that don't have a neocortex, birds, for example, don't have one. They have a similar structure, though. Can't remember what it's called. They have a similar structure in their brain that's also full of feedback loops. So is a parrot conscious? Probably is, right? Have you ever seen any of the videos of like African gray parrots? Where they ask it, like, bring me the blue donut, and it'll look around its enclosure, and there'll be like a yellow one, and it'll pick up the blue one, and it'll bring it over to you. Right? Bring me the yellow square. There isn't one. It will actually say that. Right? There isn't one. It's parroting, right? That's where we get the term. But is it aware of what it's doing? It probably is. Because it has that structure in the brain. So I think a truly intelligent AI would probably need to have a different sort of structure. The kind of large language models, they are almost all feed-forward systems. they implement even something like a recurrent neural net, which is an earlier model. It went through the different layers sort of one by one, step by step. That's not what our brains do. It's constantly bubbling. It's very, very, very messy and very, very, very noisy. Right? That seems to be necessary. Not that it has to be biological, but that I think it has to have the right kind of feedback. Right? And part of that feedback comes from having a physicalness to it, that I think large language models, if they are embodied, but they don't move. And I think that's kind of important. And they don't get sensory input. Right? So from everything from visual processing, the role of, to conscious awareness, the role of feedback seems to be very important. We have how the visual cortex is pretty much figured out. And that is a neural network, and it is a lot of feed forward, but there's also a lot of feedback. Some of the upper layers can feed back down to the lower layers and actually help you make a prediction about what's going to happen next. Right? And that's being able to predict what's going to happen next seems to be a key part of conscious awareness. So that would be what is usually called strong AI. And that's, some AIs do have some kind of awareness, right? A self-driving car, a Waymo, Starship robot, it has to know where it is on campus, right? It has to be able to figure out the quickest way to get somewhere. But if you've seen them walking around, how intelligent are they? About as intelligent as a squirrel. I think a squirrel might be actually more intelligent. So you also have AIs that learn by playing against versions of themselves. Right? That's a very common way. That's how the Go AI, it played Go against other copies of itself, hundreds and hundreds and hundreds and hundreds of times. But it never once wondered who it was playing against or what it was playing against. A human would, right? If you were constantly playing a game of Go, you would wonder, well, who's my opponent? And you would probably figure out, I seem to be playing against a version of myself, right? We have this kind of curiosity about the world. That's what I think generative AI is lacking, is a kind of curiosity. It would never spontaneously ask you what it is like to be a human being. The first thing people did with ChatGPT was ask it questions about, how do you feel? What are you? We're very curious about that. It's never going to turn around and say, how's it feel to be human? Why do you guys have to sleep every day? What's up with that? That seems weird, right? You have parents. What's that about? Children. What is that? Right? These are concepts that it should be curious about because it's sort of alien to them, right? But these are the kind of questions that a child would ask. That goes back to the idea of a child AI. If it were truly a child AI, it would ask the kind of questions kids ask. Right? Why is the sky blue? Why this? Why that? Why this? That's that kind of curiosity. And I think that's sort of what's missing in some of these systems. And I think to get that, they would probably need to be built with a different architecture. I don't think the large language model architecture is going to become like a true artificial general intelligence. Their structures, not only is it different than ours, how do we do this, right? We have this brain up here that uses very little energy. Right? It can't hold nearly as much information as a large language model, and yet it can converse, it can drive a car, it can ask questions, right? So I think one way to get to an artificial general intelligence, and this is I think where Kurzweil comes in as well, is try to build systems that actually operate as the brain does, neuromorphic computing, which there's a lot of work in that now. We already have, I'm about out of time, but yeah, we already have an implant that can replace a damaged hippocampus, part of the brain. Right? And the hippocampus is memory. People with damaged hippocampus can't form new memories. So there's now a hippocampal prosthesis. It reads the inputs, processes them, feeds them back in, and then people can start forming new memories. It actually works. Right? It's actually replacing a part of the brain with something that is doing what that part of the brain does. That's pretty exciting.
And what is this, like a chip?
Oh, no, it's outside the brain. Right now,
Okay.
the idea is eventually you want to get it down to a chip.
Yeah.
But right now, it requires electrodes going into your brain.
Okay.
Right? But it helps with memory formation. It improves it by about 50%. And that's brand new. Right?
What is that called?
It's a hippocampal prosthesis. And hippocampal prosthesis. When they were first developing it, like 5 years ago, it worked in rats. And when I went to look it up this year, it's in human trials. I mean, that's how quickly it's working. But right now, it's this big block that sits on your head, right? And they can't leave it implanted, right? Because it's invasive. You get that down to a chip, yeah, you could replace a damaged hippocampus with a computer chip, and it works. Right? That's actually, I think that's more along the roads towards an artificial intelligence. I think that's probably the path, rather than a large language model that uses, kilowatts of energy. We use so little energy, right, to do our calculations. I think we probably need to take more inspiration from how do we do it and try to build that. Right? Questions? It's 6 o'clock already. I'm sorry. Okay.